Ask any hiring manager. If you can't explain the OSI model or rattle off the top 12 must-know ports, your IT interview is over before it starts. The brutal truth? Most candidates stumble on exactly these fundamentals. This video fixes that. Zero fluff, just real, actionable networking know-how you can use this week to move your career forward. Let's go. By the end of this video, you'll have a clear map of the networking essentials every IT pro needs. We'll break down the OSI model, the real-world TCP/IP stack, the difference between TCP and UDP, MAC addresses, the big three hardware pieces, switches, routers, firewalls, along with VLANs and VPNs. And we'll lock in the 12 ports you'll see in every interview and help desk ticket. Grab a notepad. As we go, write down each topic and test yourself tomorrow. That's exactly the kind of practice that sticks. A network is simply two or more devices, computers, phones, servers, connected so they can share data and resources, like an internet connection, a printer, or files. That connection can be through an Ethernet cable or Wi-Fi. The classic beginner mistake is thinking a single PC with internet access is a network. It's not. A network requires at least two endpoints talking to each other. For example, a small office with 3 PCs hooked into a switch using one shared printer is a basic network. That setup saves that business thousands of dollars a year compared to buying separate internet lines and printers for every desk. Take a look at your own home. Your router and the devices connected to it already form a network. Networks come in 3 sizes. A local area network, or LAN, covers a single office or building, high speed, low latency, and you own the gear. A metropolitan area network, MAN, spans a city, like connecting branch offices across town. And a wide area network, WAN, links geographically distant sites, often across countries. A perfect real-world example. A company connects its LAN in London to its LAN in Tokyo via a leased line WAN that travels thousands of miles. That WAN link is slower and more expensive than your internal LAN, but it's essential for global business. When you design a network, always start by drawing these 3 tiers. It prevents chaos down the road. But here's the part. Almost everyone gets wrong about why networks exist. It's not just about getting online. The real reason is resource sharing. Instead of each employee burning a separate internet line, a separate printer, and a separate file server, which would be chaos and cost a fortune, a network lets many users share one of each. Picture a small business with 15 staff, a single business-grade fiber connection, one central file server, one network printer. Running individual connections for everyone could get prohibitively expensive, while sharing slashes costs dramatically. Put resource sharing at the heart of every network decision you make. It's the business reason that justifies the tech. Topology describes how devices are physically connected. The old bus topology used a single cable. If it broke, the whole network died. Ring topologies circulated data in a loop. A single break could disrupt the entire ring, though some designs added redundancy to bypass failed nodes. Today, the star topology is king. Every device plugs into a central switch. One bad cable only takes out one device, not the entire office. For critical systems, mesh adds multiple redundant paths. Think data centers. The biggest beginner trap is thinking all networks are star by default. Knowing these shapes helps you troubleshoot physical issues. Next time you stare at a switch full of blinking lights, you're looking at a star. Right now, mentally map your home network. Chances are it's a star centered on your router. Wired Ethernet, Cat6 or Cat6a, gives you real gigabit speeds, up to 10 Gbps, with extremely low latency, and it's immune to radio interference. Perfect for servers, security cameras, and any high-traffic backbone. Wireless Wi-Fi 6 is incredibly convenient. No cables, total mobility, but latency jumps to about 10 milliseconds, and a microwave or concrete wall can tank the signal. The non-negotiable rule: always connect servers and core switches via wired connections. I've watched networks grind to a halt because someone thought running a production server on Wi-Fi was fine. Save wireless for laptops and phones where mobility matters more than absolute speed. Next time you set up gear, wire the infrastructure first. Back in the 1980s, networking was a Tower of Babel. Novell's SPX, Apple Talk, IBM's SNA, each vendor spoke a proprietary language. A Dell PC from one manufacturer couldn't reliably talk to a Cisco switch from another without a lot of custom code. The industry needed a common reference, so the ISO created the Open Systems Interconnection Model. 7 layers that describe how data moves from your application down to copper or fiber and back up. OSI isn't a protocol suite, it's a blueprint. But knowing it gives you a universal language for troubleshooting. Is it a Layer 1 cabling issue or a Layer 7 application misconfig? In interviews, being able to walk through the layers puts you ahead of the other 80% of candidates. Burn these 7 layers into your brain. From bottom to top, physical, cables, fiber, voltage levels. Data link, MAC addresses, switches, frames. Network, IP addressing, routing. Transport, TCP, UDP, port numbers, flow control. Session, manages dialogues between applications. Presentation, encryption, compression, data translation. Application, HTTP, DNS, FTP, the services you actually use. Remember the mnemonic, please do not throw sausage pizza away. This model is a troubleshooting roadmap. Start at Layer 1 and work upward. Grab a sticky note right now, write the layers in order, and test yourself tomorrow morning. That's the repetition that ingrains them for life. Here's the mapping that confuses most beginners. The OSI model has 7 layers, but the internet doesn't run on OSI. It runs on the TCPIP model, which uses only 4 layers. TCPIP's application layer merges OSI's top 3: application, presentation, and session. The transport layer maps cleanly. The internet layer matches OSI's network layer. And the network access layer combines OSI's physical and data link. Every IP packet you send or website you visit follows the TCP/IP stack. You'll still get grilled on the OSI model in interviews and certification exams, but in the real world, you live in TCP/IP. Open the CCNA study guide later today and find the side-by-side diagram. Physically trace the mapping with your finger. That muscle memory makes it stick. Now let's talk about encapsulation, because this is where your application data actually gets dressed up for the trip across the wire. Think of it like preparing a package for shipping. You start with the raw item. That's your application data. As it moves down the TCP/IP stack, each layer wraps it in a new header, a label containing instructions for the corresponding layer on the receiving end. At the transport layer, TCP adds its header, turning the data into a segment. The network layer wraps that segment in an IP header, creating a packet. Finally, the network access layer slaps on an Ethernet frame header and trailer, producing the frame, the full shippable unit that actually hits the copper or fiber. This layered dressing is why a frame contains a packet, which contains a segment, which contains your data. No layer reads another's header, but every layer depends on the one beneath it. Let's lock in what we've covered so far. At which OSI layer does a router make its forwarding decisions? Most people think networking is all about IP addresses and routers, but here's what nobody tells you. Without the right physical cable, your entire network falls apart. At Layer 1, we're dealing with the actual physical medium, copper or fiber, voltages or light pulses. Let's look at the 3 workhorse cable types you'll encounter in a modern enterprise. Cat5e twisted pair copper supports up to 1 gigabit per second at a maximum segment length of 100 meters. It's still the minimum spec for new installs. Cat6 also does 1 Gbps up to 100 meters, but it can handle 10 Gbps for shorter runs up to 55 meters, thanks to better shielding. And then there's fiber optic, immune to electromagnetic interference, able to carry 100 Gbps or more over kilometers. That's why you'll see fiber used as the backbone between switches in a building or between data centers. Know these 3, and you can already start reading the blueprint of a physical network. Open a command prompt right now and type ipconfig all. Scroll down to your Ethernet or Wi-Fi adapter and look for the line that says physical address. That 6-byte hexadecimal string, something like 0C1A, 2B, 3C, 4D, 5E, is your network interface card's MAC address, burned into the hardware at the factory and unique worldwide. You can also use the shorter getMAC command to see just the addresses. This is the address your local switch uses to decide where to forward frames, and no two NICs in the world are supposed to have the same one. A MAC address isn't just a random string, it's structured. Typically a 48-bit identifier, with the first half often assigned to the manufacturer and the second half to the specific device. This makes MAC addresses globally unique, which is why switches can use them to forward frames accurately on a LAN. Keep in mind that MAC addresses operate at layer 2, and they don't leave the local network segment. A switch doesn't just magically know where every device lives. It learns. When a frame comes in, the switch looks at the source MAC address and records which port it arrived on in its MAC address table. If the destination MAC is already in the table, it forwards the frame only out that specific port. But if the destination is unknown, say the first time A talks to B, the switch has to flood that frame out of every port except the one it came in on, just like an old hub. As soon as B responds, the switch sees B's MAC on port 2 and adds it to the table. From then on, traffic between A and B is switched unicast, no flooding. The table entries age out after a default of 300 seconds of inactivity, so the switch doesn't hold on to stale information forever. This is the single biggest efficiency improvement in networking history, the move from hubs to switches. A hub is a layer 1 device. Every bit that comes in is simply repeated out every other port. All devices connected to a hub share the same collision domain, so if two devices transmit at the same time, their signals collide and everyone has to wait and retransmit. Worse, hubs operate in half duplex. They can't send and receive simultaneously. A switch, on the other hand, is a layer 2 device that looks at the destination MAC address and forwards the frame out only the port that connects to that device. Each switch port is its own collision domain, and switches support full duplex, meaning they can send and receive at the same time with no collisions. Swapping a hub for a switch instantly turns a congested, collision-prone network into a quiet, high-speed one. Beginners often confuse the two addresses every device has, so let's make it crystal clear. The MAC address is burned into the network interface card at the factory. It's like your first and last name. It's used only on your local network segment to decide who gets what frame, and it never leaves that local segment. The IP address, on the other hand, is logical. You can manually assign it, a DHCP server can assign it, and it can change whenever you move networks. It's like a postal address that routers use to move packets from one side of the world to the other. So remember, MAC is local, stitched into the hardware. IP is global, maintained in software. Both are needed. The IP header tells the packet where to go. The MAC header tells the frame which next hop device to pass it to. Before we break down an address, look at this chart. The more subnet bits you borrow, the fewer hosts you get. A24 gives 254 usable hosts, A28 only 14. For our classic 192.168.1.10 with mask 25 feet off, 5.10, that's EO24, the first 3 octets identify the network, and the last octet identifies the host. Network address is 0.0, broadcast 0.255, so you get 254 usable, 0.1 to 0.254, that's the foundation. Subnetting is where people often stumble, so let's do a concrete R28 example. Take the network 192.168.1.0 with a default 24 mask. If we borrow 4 host bits to extend the network portion, our mask becomes 28, 255, 25, 2555, 240. That gives us 2 to the 4th power equals 16 total subnets, each with 4 bits left for hosts. 2 to the 4th is 16 addresses per subnet, but you lose 2. The first address is always the network identifier. The last is always the broadcast. So each subnet gets 14 usable host addresses. The first subnet is 192.168.1.28, hosts 0.1 through 0.14, broadcast 0.15. The next subnet starts at 192.168.1.16 to 28, and so on. The number one beginner trap is forgetting to subtract those two addresses, so always remember, network and broadcast are off-limits for hosts. When your PC wants to reach anything outside its own subnet, say 8.8.8.8, it doesn't just shout into the void, it checks its routing table. On Windows, you can see it with rootprint. The entry that matters most is the default route, 0.0.0.0 mask.0.0.0.0, which points to your default gateway, usually your home router at 192.1168.1.1. That IP is the exit door for any destination that isn't local. The common trap beginners fall into, thinking the PC connects directly to the internet. Without that gateway configured, no internet, period. But here's the part. Almost everyone gets wrong. Your data doesn't just magically go to the internet. It gets stripped and rebuilt frame by frame. Watch the MAC addresses at each hop. From PC to router, the source MAC is your PC. Destination MAC is the router. The router then rips off that layer 2 header and creates a brand new frame for the next hop, with its own MAC as source and the ISP router's MAC as destination. All the while, the source IP 192.168.1.10 and destination IP 93.184.2.16.34 example.com stay exactly the same. The internet routes by IP, not MAC. This re-encapsulation is the visual proof that routers work at layer 3, not layer 2. Before we move up the stack, here's a common pain point. A huge number of help desk tickets for "the internet is down" trace back to a missing or misconfigured default gateway. Now, quick recall. What job does that default gateway actually do? Now we hit the transport layer, the fork in the road. You need to decide reliability or speed. Here's a real-world IT ticket I've seen. The internet is slow on the 3rd floor. You dig in and find it's a TCP retransmission storm because a switch port is throwing CRC errors. That's the transport layer screaming at you. Get this choice wrong, and you're the one opening a P1 ticket. TCP ensures every byte arrives in perfect order. UDP fires it off and doesn't look back. A file download values correctness. A live voice call values timing. This is where the network engineer's intuition is forged. TCP builds a reliable pipe before sending data, a 3-way handshake, sequence numbers, acknowledgements, and retransmission. That makes every web page and email download reliable. UDP fires data and doesn't look back. One missed voice packet in a call? You wouldn't want it resent 200 ms later. By then it's useless. DNS uses UDP for quick lookups, port 53, though zone transfers can use TCP. That nuance trips up beginners who think DNS is strictly UDP only. Every TCP connection begins with this 3-step dance. Client sends a SYN packet with a random sequence number. Server replies with its own SYN and an acknowledgement of the client's sequence, SYNAC. Client then ACKs back, and now both sides are established. This happens in milliseconds every time you load a web page. Beginners often mistakenly think TCP creates a physical circuit. It's purely a logical handshake over IP, but the reliability it forces is very real. All these everyday services choose UDP because a delayed packet is a dead packet. In a live stream, if a frame is lost, you'd rather see a tiny glitch than wait for a retransmission that arrives after the next 30 frames. In a game, resending a position update from 50 ms ago would make your avatar teleport backwards. UDP trades reliability for immediacy, and for these applications, that's exactly the right trade. Imagine a high-rise apartment building. The IP address is the street address of the building, 203.0, 3.5. But that building has hundreds of apartments, and simply arriving at the building doesn't tell you which resident to visit. Port numbers are the apartment numbers. One server at a single IP can run a web server on port 80, an email server on port 25, and SSH on port 22, all reachable at the same IP, but completely separate by port. That's how 203.0.1, 113.55.443 knows to deliver your browser request to the HTTPS service, not the SSH daemon. Knowing common port numbers is like having a map of network traffic. Being able to instantly recognize what service a port belongs to will make troubleshooting and interviewing much faster. Spend 5 minutes a day drilling them with flashcards. It's a small investment that pays off immediately. Time for instant recall. You just saw the common ports list. Now without looking, which port number does SSH use? Need to quickly check if a domain resolves correctly? ENS-lookup is your first tool. Fire up a terminal and type ENS-lookup google.com. You'll see the DNS server you're querying and, most importantly, the resolved IP address. This is an instant sanity check. If you see an IP, DNS is working. The response might say non-authoritative because your local resolver cached it. An authoritative server gave it to your resolver earlier. You can also use NS-lookup type MX to find mail servers. This command lets you verify name resolution instantly, a fundamental step in network troubleshooting. Now, how does that resolution happen behind the scenes? A common mistake is thinking your computer talks directly to Google's DNS server. In reality, your PC sends the query to a local DNS resolver, often your router or your ISP's server. That resolver then does the legwork. It first asks a root server, which doesn't know the IP but knows where to find .com servers. Then it asks a .com TLD server, which points to Google's authoritative name server. The authoritative server finally returns the IP. Crucially, the resolver caches this IP so future queries are lightning fast. So the whole process is query hits, resolver, root, TLD, authoritative, all in milliseconds. Without DHCP, you'd manually type a unique IP, subnet mask, and gateway on every device. A recipe for errors. That's why we use the DORA process. Discover, offer, request, acknowledge. Your computer broadcasts a discover packet, shouting for an IP. A DHCP server hears it and sends an offer with an available IP, say 192.168.1, 1.50. Your computer then broadcasts a request, confirming that offer, and the server sends an ACK finalizing the lease. Typical lease time is 8 days, after which the device must renew. This automated handshake is what gets you online instantly when you plug into a network. Here's something that should keep you up at night. Many cloud security breaches involve firewall misconfigurations, not zero-day exploits. That's why you must understand packet filtering inside out. A firewall inspects the source, destination, IP, port, and protocol of every packet, then applies a rule set. By default, a properly configured firewall like Windows Defender blocks all unsolicited inbound traffic, packets from the internet trying to reach your PC, while allowing outbound connections you initiate, like browsing the web. It also logs dropped packets so you can spot attacks. The golden rule: allow outbound, block inbound by default. Get this wrong and you're relying on luck, not security. Firewalls come in 2 flavors, and you need both for defense and depth. A software firewall runs on your host, Windows Defender or IP tables, protecting just that device. A hardware firewall is a dedicated appliance, Cisco ASA, Fortinet, Palo Alto, that sits at the network edge and handles stateful inspection at scale, tracking many concurrent connections to automatically allow return traffic. But here's the hidden risk. Even expensive hardware firewalls are useless if misconfigured. A large percentage of firewall breaches are traced to human misconfiguration, not a missing vendor patch. The real-world strategy: use software firewalls on every endpoint and a hardware firewall at your perimeter. If one fails, the other still protects, assuming both are configured correctly. How can your laptop, phone, and smart TV all share one public IP? The answer is network address translation, specifically PAT, port address translation. Your laptop with private IP 192.1168.1.5 sends a packet from source, port 1234. Your home router sees it, creates a NAT table entry, and rewrites the source to its public IP 203.113.5 with a new unique port, say 5000. When the reply hits port 5000, the router maps it back to your laptop. This works for outbound connections only, which is why you need port forwarding to host a public game server at home. PAT conserves IPv4 addresses and is the reason billions of devices coexist behind a few million public IPs. Why did we invent NAT in the first place? The internet was built with IPv4, which offers about 4.3 billion addresses. Sounds huge, but with billions of people and devices, we ran out. NAT was the emergency fix. By using private IP ranges defined in RFC 1918, 10.0.0 Mursaspawait, 172.16.0 and 192.168.0 devices talk internally with those addresses and share one public IP when reaching the internet. A single NAT router at home or the office can translate traffic for thousands of devices. That's why your phone, laptop, and smart TV all work behind one broadband connection. Inside a company, you often want to isolate departments. That's where VLANs, virtual LANs, come in. On the same physical switch, you assign ports 110 to VLAN 10 for engineering and ports 1120 to VLAN 20 for marketing. Even though they're plugged into the same hardware, a device in VLAN 10 cannot send a packet directly to a device in VLAN 20. They're in separate broadcast domains. To allow communication, you must add a router. This is inter-VLAN routing. VLANs also reduce unnecessary broadcast traffic. An ARP broadcast from an engineering PC stays in VLAN 10, never flooding marketing, improving both security and performance. But how does a packet from VLAN 10 on switch A reach the same VLAN on switch B across a single cable? The answer is 802.1q trunking. When a frame leaves switch A, the switch inserts a 4-byte tag into the Ethernet header with the VLAN ID, say VLAN 10. The receiving switch reads that tag and forwards the frame only to ports belonging to VLAN 10. That way, one physical trunk link can carry traffic for multiple VLANs simultaneously, each frame carrying its own tag. Without 802.1q, you'd need a dedicated cable for every VLAN. Impossible at scale. This is how we virtualize many networks over one wire. When a remote employee needs to securely reach the office, a VPN creates an encrypted tunnel across the public internet. Protocols like IPsec or SSL/TLS encrypt the entire packet, so even if someone intercepts it, they can't read the data. The employee's laptop appears as if it's sitting on the corporate LAN with a private IP. That means they can access internal file shares, printers, and applications just like they're in the office. VPNs are the backbone of modern remote work. Without them, secure connectivity over untrusted networks would be out of reach. Let's make this concrete. You're at a coffee shop on the open guest Wi-Fi, no VPN. The network is unencrypted. Every website you visit, every DNS query, every unencrypted credential is visible to anyone running a free packet sniffer. Even HTTPS doesn't hide what domains you're looking at. Now turn the VPN on. Your traffic gets wrapped inside an encrypted tunnel that terminates at the VPN gateway. The barista's rogue AP can't see a thing, and you can suddenly access internal file shares on port 445 as if you're plugged into the office switch. That one toggle is the difference between a career-ending data leak and a secure workday. Use a VPN every single time you connect through a network you don't own. Here's a mistake I hear from almost every beginner. My home router has NAT, so I don't need a firewall. NAT, Network Address Translation, was invented to conserve IPv4 addresses, not to secure a network. It rewrites the source IP of outbound packets and keeps a translation table. That's it. It doesn't examine what's inside the packet. It doesn't stop an attacker who already has a foothold from exfiltrating data. And it won't block a malicious inbound connection if the destination port happens to be mapped. If you rely on NAT as your only defense, your network is one port forwarding rule away from being wide open. You still need a firewall with explicit deny all else rules and layer 7 inspection, period. These port numbers aren't just trivia. They're the beachheads attackers probe first, every minute of every day. SSH on port 22 and RDP on 3389 top, the list for relentless brute force attempts. HTTP and HTTPS follow close behind, hammered by vulnerability scanners. SMB on port 445 still echoes eternal blue. Lock down just these ports with strong authentication, MFA, and firewall rules that restrict access to only trusted IPs, and you've already eliminated the vast majority of opportunistic threats. Here's what nobody tells you about memorizing port numbers. It's not for the exam. It's for the moment your paycheck depends on it. Picture this. It's your first week as a junior admin. The file server is down, the whole office is dead in the water, and the boss is standing behind you, arms crossed, asking, "Why can't anyone access the shared drive?" You open PowerShell, type test net connection, port 445, and the result is TCP connect failed. In 2 seconds, you know SMB is unreachable on the critical port. You check Windows Firewall, see the inbound rule is missing, you enable file and printer sharing, and suddenly everyone's back to work. The senior engineer who was about to be called after hours? You just became the person they don't need to call. That's career currency. And it starts with knowing what a single port number does. If you're walking into an entry-level help desk or ENOC interview, expect these 5 questions to come up in some form. You don't need a 10-minute dissertation, just a crisp, accurate answer that shows you understand the why, not just the what. The TCP three-way handshake proves you know how connections are built. TCP versus UDP shows you can pick the right transport for the job. VLANs demonstrate you know how to segment a network beyond just plugging cables in. DNS is the core service that makes the internet usable, and connecting it to real-world troubleshooting, like DNS is not a resolution problem, makes you stand out. And if you stammer on, "What port is HTTPS?" the interviewer will assume you skipped the fundamentals. Practice these answers out loud until they feel conversational. Here's the concrete action step. Stop putting off port memorization. The #1 rookie mistake is telling yourself you'll learn them later, and then freezing in an interview or on a troubleshooting call. Grab a stack of index cards right now. Write the 12 critical ports we covered: 22 SSH, 80 HTTP, 443 HTTPS, 3389 RDP, 445 SMB, and the rest, dual-sided. Spend 10 focused minutes a day for 1 week. That's it. Your brain works best with spaced repetition. By day 7, those numbers will be as automatic as your own phone number. This one habit turns book knowledge into career reflexes. Let's walk through the exact diagnostic flow when a user can't reach a file share. You map a drive using the server's name or IP, and it fails. First instinct. Open PowerShell and run test net connection, port 445. If you get a failure, SMB isn't reaching the destination. The most common reason on a Windows host is that the built-in Windows firewall is blocking inbound SMB, which uses port 445. You go to Windows Defender Firewall, find the file and printer sharing rule, and enable it for the appropriate profile, domain, private, or guest network. Immediately, the share lights up. But here's the twist many beginners miss. Even if the server allows inbound SMB, the client's own outbound firewall might be blocking 445. Verify outbound rules on the source machine, too. That one extra check saves hours of head-scratching. If you're studying for CompTIA's Network Plus exam, code N1009, or Cisco's CCNA 200-301, you just covered a massive chunk of the objectives: the OSI model, encapsulation, IPv4 subnetting, TCP UDP behavior, VLANs, DNS, DHCP. These are the exact topics that show up in the exam objectives and also in real-world job interviews. Use this video as your conceptual baseline, then go build it in Packet Tracer. That combination of theory first, then hands-on, is the fastest path to passing the exam and actually being able to do the job. You don't need to spend $1 to keep going. Bookmark networklessons.com. It covers every CCNA topic with visual, step-by-step lessons. Search Professor Messer's Network Plus playlist on YouTube. His free series is the gold standard for exam prep. If you want deeper theory, grab Firuzan's Data Communications and Networking, widely recommended as a textbook that explains the why behind every protocol. And download Cisco Packet Tracer. It's free. It lets you build networks with virtual routers, switches, and PCs, and it's the best way to turn the concepts from this video into CLI muscle memory. Put at least 1 hour into Packet Tracer this week, even if it's just setting up a simple LAN. Last recall check. When you're asked in an interview or a troubleshooting call what service runs on port 3389, you need to answer immediately. Remote Desktop Protocol, or RDP. That's how you remotely control a Windows desktop, and it's one of the most attacked ports on the internet. If you can rattle off 3389 without hesitation, you've cemented the must-know port list. Now go download Packet Tracer and apply everything you've learned, because knowing isn't enough, you have to do. Before you click away, grab the free IT Career Roadmap linked in the description. It's not just a list of topics, it's a step-by-step networking study plan, a breakdown of which certifications employers actually look for, like CompTIA Networks and Cisco CCNA, and proven job search strategies that have helped people with no experience land their first IT job. Don't just watch this video. Download the roadmap and start your first study session this week. I'll see you in the next one.